All right, welcome back to part 2 of our area lesson. And just a quick reminder in case you've done something else in between, when we did that area lesson, all we talked about is that if you take the integral from a to b of f of x minus g of x dx, what it's going to give you is it's going to give you the area between two curves where f of x is on the top, g of x is on the bottom, in between values of a and b. So the integral of f of x minus g of x being top minus bottom gives you the area between two curves on a graph. So moving forward in our notes packet here, we left off at example 6. And the reason I left off here is an important one. If we look at this area enclosed between y equals x cubed and x equals y squared minus 2, when I go to shade in this region, it looks sideways this time. And we have one of our functions in y equals form and another function in x equals form, and that's just a little bit odd. So one of the things I want to show you in this is if you have a region that looks sideways, what you're going to do is you're going to look at your representative rectangles at first and say, okay, my first representative rectangle goes from the, let's see, this parabola, this sideways parabola, to this cubic. But then over here, all of a sudden, I have a rectangle that's bound by one curve and itself. And then I got to separate it here. This looks like a big pain in the neck. So what we can do instead is say, all right, instead of our rectangles being bound by different things at different times, what if I drew my rectangles this way? And said, all right, my representative rectangles are going to go from right to left instead of top to bottom. Well, if I have a rectangle that's oriented right to left, the height of the rectangle is this distance right here, and the width of the rectangle is that distance right there. And this distance is a minuscule value of height, which is now going to be dy. And that's our indication that, hey, now we're going to write integrals with respect to y instead of with respect to x. Well, if I'm doing stuff with respect to y, that means all the stuff in here needs to be in terms of y. So that means I need my functions in terms of y. So this function right now is a y equals in terms of x. So if I take y equals x cubed and rewrite it, I would have to rewrite it as x equals the cube root of y. No plus or minus needed. This is an odd root. So x equals the cube root of y is going to be this right here. And then x equals y squared minus 2 is already in terms of y. Now, we used to integrate top minus bottom if I was integrating with respect to x, but when I'm integrating with respect to y, instead we're going to do right minus left. And another thing that's important is since we're in terms of y, that means these need to be y values. So I need y boundaries for whatever this is and whatever that is. I'm going to use my calculator to figure it out. So when we want to integrate this one, what it's going to end up looking like is the integral of right minus left. So on this region, this y equals x cubed, in other words, x equals the cube root of y, is on the right. And then on the left, we have this sideways parabola, which is y squared minus 2. And now I need to figure out where they intersect. And you're probably thinking, well, how am I going to graph it? My calculator only graphs things if they're in y equals form. Well, you know what? Just trick your calculator. In your calculator, graph y equals the cube root of x and y equals x squared minus 2. Figure out where they cross. And that's just going to be where these graphs cross. So if I graph the cube root of x in my calculator, it's going to look something like that. And x squared minus 2 is going to look something like this. Whatever these two x values are is the same as the y values that you need over here. So if you go to your calculator, you graph those two things, you figure out where they cross, you are going to get values of -1 and another value, this one right here, is 1.793. And now I just have to integrate this. using the calculator. And you're thinking, again, my calculator only says x, Mrs. Vibber. Well, that's fine because your calculator doesn't care if this is a y, an x, a theta, doesn't matter at all. It's a dummy variable. So when you put this into your calculator, all these y's are going to become x's anyways. Throw that into your calculator, you get 4.215. Now I'm going to backtrack a little because I did that pretty quickly. Long story short, what just happened is if you have a graph that looks sideways, so instead of top to bottom, it's right to left, all you're really going to do is you're going to integrate right minus left and put everything in terms of y instead of x. But when you type it into your calculator, use an x instead. So let me show you again how we can do that. Find the area in the first quadrant bound by y equals the square root of x. And wait a minute, this one looks pretty similar to what we did before. Well, I did that on purpose. When we did this area before, when we graphed it, I had the square root of x, I had x minus 2 here. I had to separate this because my representative rectangles, when I did them vertically, I needed two different kinds. I had one rectangle that looked like this and one rectangle that looked like that, and I needed two integrals because one is bound on the top by the cube root and then the line, I'm sorry, square root and the line, and then over here by the square root and the x-axis. Well, if my rectangles need to change partway through, sometimes that means you can separate the integral, but to make your life even easier, why not write a single integral, writing your rectangles the other way? If I drew all these rectangles in left to right, they all are bound by the line and the parabola. Well, if I do them left to right, that means I need to integrate with respect, pardon me, to y. So then I need to figure out where these cross in terms of y. Well, that bottom is y equals 0. And on top, we said before that they intersected, I believe, at, let's make sure, x equals 4. So if x equals 4, the square root of 4 is 2. So I'd have the integral from 0 to 2 of right minus left in terms of y. So my right curve is the curve y equals x minus 2, which in terms of y becomes x equals y plus 2. And then my left curve is the square root function. So if I have y equals radical x, that means x equals y squared. I have that. I plug it into my calculator, but I use x's instead. And your calculator should tell you, voila, the same thing we had before, 3.333. Okay? Long story short, those last two look kind of confusing, but all you have to do is switch all the y's into x's and you're good to go. Now is where it gets really interesting. The only thing that can make it better is logarithms because I love them. So find the value of k, okay, such that the line x equals k divides the area enclosed by that into two regions of equal area. I can use my calculator, so I'm going to graph it. So I have y equals x squared. Let's put this one in first and maybe see what they're talking about. And then y equals 6 minus x, which looks something like this. Again, this is just a sketch. And that's the area enclosed. So I have this area right here. And they're saying find the line x equals k so that this is split into two regions of equal area. So what I want to do is figure out where to put this line so that it splits the region into two separate parts with equal area on either side. All right, so I understand what they want me to do, but now we need to figure out how do I do that. Well, the first thing I want to do is probably figure out these boundaries because that seems important. So when do x squared and 6 minus x equal each other? If I just solve the quadratic, I'm going to have plus 3 minus 2. So x equals negative 3 and positive 2. Okay, so I know k needs to be between those two values. Hey, that's something. And what I really want to have happen is I want the area from -3 to k of top minus bottom to equal the area from k to 3. Nope, sorry. From k to 2, I got 3 happy, of top minus bottom. That's one way to look at it. But the problem is I have k's on both sides, and that's kind of annoying. So option 1 is to set this up and go from here. But I'm going to give you an even better option. Option 2 is to say I still want the area from -3 to k. I want that left part. But what I really want is I want the left part, this thing right here, I want this left part to be half of the whole thing. And now the benefit here is since I can use my calculator, I can put this into my calculator and not have to integrate that right-hand side by hand. So I'm absolutely going to do that right away. I'm going to plug it into the calculator. It's going to give me some decimal value, which I am going to convert into a fraction. If you want to know the decimal, you can do it yourself. But you put this into your calculator, you get 125 over 12. What do I do with the left? I don't know what to do with the left, but you know what? All I can do is integrate. It says I can use my calculator, but my calculator's not going to let me put this k in. So this part we have to do by hand no matter what. So I'm going to take the antiderivative, and I'm going to evaluate it at -3 into k. Well, how do I evaluate it at k? I just plug k in, same way I always do. So 6k minus 1/2 k squared minus 1/3 k cubed minus what I get when I plug in -3, which is going to be -18. Let's see, minus 9/2, and then plus 9. And at this point, now all I'm doing is I'm solving this equation for k. So now I'm going to use my calculator again. If you want to use your calculator to solve an equation, my rule is just always set it equal to 0. So subtract 125 over 12 from both sides to set this side equal to 0, blah, 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 minus 125 twelfths. Graph this in your calculator. So graph 6k minus 1/2 k squared using an x. Put this whole left side into your calculator. See where it crosses the x-axis, which is when it's going to equal 0. And your calculator should show you that it crosses the x-axis at x equals -1/2. Again, this last part, it looks like I did some magic, but all I did was evaluate it and then use my calculator to plug it in and solve the resulting equation. That's a tough one, but it's fun. All right, so finding the areas of regions R and S, I'd like you to do that on your own. If you want, maybe hit pause on the video for a second, try it on your own, and then come back to me. The way that we solve this is exactly what I'm about to write on the board. So I want the integral of tan x dx plus the integral of 2 minus x cubed dx. And that's going to give me r. Now this a I put here is just going to be a value that I calculate, and I usually store it in my calculator. So I'm going to throw these two integrals into my calculator, and they're going to tell me 0.729 is the answer. There's the area of R. And then for S, I don't need two separate integrals. I can just do the integral from 0 to a of 2 minus x cubed minus tan x. That's a top minus bottom again. And if you plug that into your calculator, you're going to get 1.161. So again, I'm not going through that. That should be something that you can do on your own based on everything we did. R needs to be separated into two regions because first, it's bound above by tan, and then the second time around, it's bound above by 2 minus x cubed. Now you might be thinking, hey, Mrs. Vibber, didn't we do that thing before where you could do them sideways? You absolutely could do that here. It's just that when you do that, in this case, when you solve this y equals tan x as an x equals, you get x equals inverse tan y, which is just kind of obnoxious to work with. So I don't put that here. You could do it, but I would probably suggest separating the integral because it doesn't really make it any harder. Okay. Find the regions of R, S, and T for the curves here, and they tell me that the curves are y equals radical x and y equals e to the negative x. Again, I'd like you to hit pause on your computer for a second and try this one on your own. Once you think you have it, unpause and come back to me. So I'm going to pause. You hit pause. And welcome back. Your area for R is going to be 0.196. Your area for S should be 0.162. And the area for T should be two separate integrals. And you get 0.471. I kept using A again because I kept using that intersection that is previously unknown. As long as you identify what A is somewhere in your problem, feel free to use it as a boundary. All right, now number 9, you can hit pause again and then come back to me. This one I will go through though because it's another one of those tricky ones. Find the value of C such that y equals C separates the area in quadrant 1 enclosed by that stuff into two regions of equal area. So if you want, hit pause. If not, keep going with me. So I'm just going to deal with quadrant 1. Y equals x squared in quadrant 1 looks like this. The y-axis is going to be another boundary, so I don't want to forget about that. And y equals 9 is going to come through here. And just to remember, I know that crosses at 3. It might be necessary to know that. So I'm taking this region right here, bounded by the y-axis and all that stuff, and I want to separate it by the line y equals c. So this is just like that one where we had x equals k before, but this time it's y equals c. So I want to figure out where that needs to go. Well, if I'm separating it in terms of y and I've got this horizontal motion, that's a really good indication that, you know what, we want to do this integral with respect to y. So I want the region from y equals 0 to y equals c to be 1/2 the area of the region from 0 to y equals 9. And now I'm going to do right curve minus left curve. So my right curve is this parabola right here, but it needs to be in terms of y, so that's going to be x equals the square root of y. So right minus left, well, minus the left is just the y-axis, so really that's minus 0. But like we spoke about a little while ago, subtracting 0 is just silly. No one does that. So then I've got 1/2 that region, and my integral on this side should be the same thing. But Mrs. Vibber said this time don't use your calculator, so we have to do this by hand. So over on this side, I'm going to have 1/2. This is y to the negative 1/2, so I'm going to add 1 to the power, divide by the new power, and then I'm going to plug in my bounds and subtract. So this is going to be 1/3 of 9 to the 3/2 minus 0 to the 3/2. And that's going to be 1/3 of 9 to the 3/2 is 27, which gives me 9. And then over here on the left, I'm going to have 2/3 y to the 3/2 again as my antiderivative. Plug in 0 and 3 and subtract. So 2/3 c to the 3/2 minus 0. So now I have 2/3 c to the 3/2 is 9. I'm running out of space here, so I'm going to kind of shift myself so that I can follow in a line. 2/3 c to the 3/2 is 9. Multiply both sides by 3/2. Do a little algebra here. This is going to be 27/2. And then I'm going to raise both sides to the 2/3 power. And you might be thinking, ew, that looks really gross. You know what? No one cares. If you're solving without a calculator, you can leave your answer just like this. If you're interested, the answer to that is 5.670 if you were allowed to use your calculator. And just for reference's sake, that seems to make sense. If I'm going to split this area from 0 to 9 up, 5.7-ish being the line that draws through, I would say that seems reasonable. So there you go. That's how you find area between two curves with respect to y and with respect to x. Enjoy the show.